To finish this section, we want to talk about lateral surface area. To get started on that, we're going to need some sort of simple shape that we can describe the surface area of in the same way that we can easily calculate the volume of a box or the area of a rectangle. In this case, the shape that we're going to use is as follows. Imagine that you had the surface of a right circular cone and then cut the end off of it so that you have this kind of shape. I'm not interested in the interior, I'm just interested in the surface of the thing. This kind of shape is called a frustum, and I want to have a formula for the area around the sides of the thing, literally the lateral surface area. Lateral means side in this case. I'm going to call the larger of the two radii capital R, the smaller one little r, and then the length along the surface of the frustum from the smaller circle to the bigger circle, I'm going to call that L. That is not the horizontal distance, not the vertical distance, but the slant distance along the surface. If you take an X-Acto knife and cut that surface in a way that's at right angles to the base and to the other end, you get a shape that looks like this. This distance is still L. The distance along this part is what you get from the circumference of the bigger circle. That'll be 2 times pi times the bigger radius. Likewise, this distance is the circumference of the smaller circle. I'm not going to make you suffer through it. A simple but long calculation shows that this area, which is the lateral area of this shape, is 2 pi times a radius value times the slant length. And by radius value, I mean any number, or a number in this case, between capital R and little r. The any number comment is going to be when we set the integral up. Imagine that you have the graph of y equals f of x, starting at x equal a and ending at x equal b. We're going to revolve this around the x-axis so as to generate some sort of three-dimensional solid shape. Though this time we're not interested in the volume of the shape, I'm interested in the number of square inches or the number of square centimeters, or whatever my units happen to be, of the lateral part of the sides of the thing. This is not including this circle, not including that circle. So what we're going to do, I'll think of a specific example, y equals x squared. I'm going to look at x going from 1 to 2, and I'm going to revolve this around the x-axis. When I do so, I'll get kind of a fluted shape here. The way we're going to calculate is the same trick that we've done with everything else. I'm going to chop the x range from 1 to 2 up into a lot of smaller subintervals, so small that I can practically pretend that the upper part is a straight line. I'll revolve that one part about the x-axis and get a shape that looks like this. Our recipe is going to be 2 pi times the radius times the slant length, not delta x, but the distance along the slanting part of the surface. That's the arc length along the graph of y equals x squared for this particular subinterval. So our new and improved recipe is going to be 2 pi times radius times arc length, in particular, gives me the slant length L for this little chunk. In a way that should surprise nobody by this stage of the game, the radius is a y-coordinate. This is exactly similar to how you would say the radius is the y-coordinate if I was going to do the disk or Warscher method. We will have 2 pi times the radius, which is the y-coordinate, times. That's how we calculate arc length on little subintervals. Do the usual thing and add them up. You'll have an integral from 1 to 2 of 2 pi times the y-coordinate on the graph we're looking at is x squared. So I'll just write the x squared in. For the little chunk of arc length, I need to write radical 1 plus the square of dy dx, and then I have to write dx down at the end. The derivative of x squared is 2x. Square that, you'll get 4x squared. So I have to calculate the integral from 1 to 2 of 2 pi x squared radical 1 plus 4x squared with respect to x. At the moment, we have no way of doing this in closed form, but I can bring out the calculator and I get 49.4162 some odd by the TI-83 or 84 method. Calculating the integral is a different task from setting the integral up. In Chapter 8, we're going to study different techniques of finding antiderivatives. After we get done with Chapter 8, we should be able to do this problem in sort of a closed form. I want to look at a slightly more abstract looking problem. If you look at the graph of x squared plus y squared equals a squared, from what we've seen back in pre-calculus, everyone knows that that's a circle with center at the origin, radius equal to a. I can rearrange it slightly. Y squared is a squared minus x squared. And then you have to be a little bit careful. Typically, for a given x value, there's going to be 2 y's to go with it. One of them is y equals radical a squared minus x squared. And you remember that the radical symbol for square root never gives you back a negative answer. So the graph of this is not the entire graph of the circle. It's the part of the circle where the y-coordinate isn't negative. So you end up with the top half of a circle. The other possibility is if y is the negative of the positive number radical a squared minus x squared, that'll make y not positive. It'll make it less than or equal to 0. So you'll get negative y values mostly, except at the ends. This is the bottom half of the circle. You can work with either one of these you wish. I'm going to work with this one so that I don't have to worry about the extra negative sign. So we're going to look at the graph of y equals radical a squared minus x squared from negative a to positive a for x values. This is the top half of a circle. I'm going to revolve this around the x-axis, and I want to calculate the surface area of the resulting shape, which obviously will be a sphere of radius a. What are we supposed to do? Our recipe is now 2 pi times radius times arc length. Divide the x range up into smaller subdivisions. On each subdivision, think of the amount of surface area that's going to be generated by revolving this little piece of the graph about the x-axis. The radius, as before, is going to be the y-coordinate. The arc length is this radical quantity times delta x. Then you have to add up all these things and take the limit. Also, we know that y is equal to radical a squared minus x squared. So the integral that you're going to have to calculate in order to find the surface area of a sphere with a radius a is integral from negative a to positive a, 2 pi square root a squared minus x squared times radical of 1 plus the square of whatever the derivative of square root of a squared minus x squared works out to be with respect to x. I'll admit it, this looks kind of horrible. We're going to have to do some intermediate calculations, but in the end, a miracle will happen. First of all, I'm going to calculate the derivative of radical a squared minus x squared. The principal square root function is by definition the same as the 1/2 power function. So I'll write it that way. I've got a function of a function. I've got the 1/2 power function, and the input into it is a squared minus x squared. In order to calculate the derivative correctly, we have to use the chain rule, which says take the derivative of the outside function. The derivative of the 1/2 power function is 1/2 times the 1/2 minus 1 power function. And you have to evaluate that at the place where you were evaluating the outside function at. So I have to write down 1/2 times the negative 1/2 power of a squared minus x squared. But there's more. The chain rule says I have to multiply by the derivative with respect to x of the thing that I was feeding into the square root function to start with. The derivative of a squared minus x squared is negative 2 times x. The 1/2 and the 2 cancel each other out. I've got a negative sign. X shows up as x to the first power, and the negative 1/2 power of something is 1 over the 1/2 power, which is 1 over square root. When the dust finally settles, the derivative of y with respect to x is negative x over radical a squared minus x squared. But we're not done yet. What I actually need is 1 plus the square of that derivative. 1 plus, when you square something that has a negative sign out front, the negative sign goes away. The square of x is x squared, and the square of the principal square root of a squared minus x squared is a squared minus x squared. To combine this into a single fraction, I'm going to write the 1 as a squared minus x squared over a squared minus x squared, so that the denominator of that fraction is the same as the denominator of the other fraction. When you add these two together, upstairs, the x squared cancels out, and you're left with a squared over a squared minus x squared. Still, that's not what we actually need. We need the square root of that quantity. When you have the square root of a fraction of two positive numbers, you can break it up into the fraction of the square roots. A is the radius of my circle. A is positive, so radical of a squared is just a, and there's no need to worry about signs and things here. Going back to the integral for the surface area, we have 2 pi radical a squared minus x squared times the fraction a over radical a squared minus x squared with respect to x. And at this moment, the miracle happens. The radical quantities cancel each other out, so they're gone. They're not an issue anymore. Even better, a is supposed to be the radius of the circle that we started off with. 2 is a constant, pi is a constant. 2 times pi times a doesn't depend on x. So an antiderivative for 2 pi a is just 2 pi a times x, then we evaluate that between x equal a and x equal negative a and subtract. And after we simplify the result, the surface area of a sphere is 4 times pi times its radius squared. This is the formula that they probably made you memorize in high school and you may have forgotten by now, but it doesn't make any difference because we can figure it out for ourselves now. This is about as much as I want to go into on the lateral surface area problems. In the next discussion, we're going to talk about work, as in the energy sense of the word work. This will finish what we're going to do in Chapter 7, and after that, we'll begin studying Chapter 8, which is techniques of integration. Basically, that's going to be a gigantic bag of tricks that you use in order to find antiderivatives, which we can't currently do anything about. In the interim, I might also make up a short discussion of the hyperbolic trig functions and show you that you can actually do some of the examples in this discussion in closed form if you know about those. Until then, I hope everyone has a good day, and I'll speak with you again